Hi, so my name is François Cornoyer.
And my name is Antoine Fortier.
And we will talk to you about a crowd of Assassin's Creed Unity that I will refer to as ACU because it's ingrained in my mind. All right, so I don't know if you've played our game or not, but we could achieve actually pretty big crowds. In this specific scene, we have 10,000 NPCs that you can actually go to and interact with. So we'll go over about the basic of our system and how we could achieve it. Don't look for like a major solution that will change your life. It's a bunch of pretty small things that allowed us to do it. Obviously, being efficient is the most important thing. All right, so first, the mandatory background slide. So a little background. It's really been in our mind since the beginning of the brand to have like these huge crowd to give life to our cities, and the player could actually be in and interact with. We felt also that it would be a social stealth ingredient that we could use. We were halfway there. I mean, we tried. We didn't succeed all the time. Actually, a big limitation was the CPU of our AI. I think of our traditional AI as like probably most AAA AIs around. So it's super complex, can do a lot of calculation and everything. And actually, because of their cost, we are only limited to 100 of them spawned at one point. So out of these 100, you obviously need guards, thieves, courtesans, and other people imported for gameplay. So for like the decorative ambient NPCs, you're left with around 20 civilians. Now, if you spread them around the loading area, you're statistically left with around 4 around the player. So it's obviously nowhere near a crowd. We could have crowds in some specific missions where we have control over the resources and everything, so we could do it, but never in a systemic way. So we were screwed. Hopefully, we integrated technology from an old prototype, and we used it on AC3 and 4. This technology actually enables us to have lots and lots of really cheap mesh that can play a single or like 1 or 2 animations. These are not entities. They are simply a visual thing that gets animated, but we can have lots of it. We use it on AC3 and 4 for the birds, the rats that you see around the street. We also used it noticeably for the Bunker Hill sequence of AC3, where there is like this big army in front of the player. But what's actually there is simple meshes, like no entity at all, simple meshes that play shoot and reload animation. So it's really cheap, but far away. And the main thing is you cannot interact with them at all. So that's what we had for AC3 and 4. So we kind of worked on a way to bring like the legacy AI with this cheap technology, and we called our new system the bulk system. So we call it the bulk system. It's like an old name that we kept using, so we're kind of stuck with it. So in here, each member is called a bulk. We don't talk about entities because not every member has an entity, so it's really a bulk. So the idea behind this whole system is pretty easy. It's to have these thousands of really cheap mesh. We have a pool of pre-spawned NPCs, like real legacy AIs. And as the player gets close to the cheap ones, we replace them with people from our pool. So around the player, he always sees our pre-spawned NPCs that acts correctly and good. And far away, he has the cheap ones. We have 3 AI LODs. We call it AI LOD to distinguish them from the usual graphic LOD because it's not only a visual change, it's also a brain change. So also, in Unity, we support co-op with 4 players, so we needed to have a way to have this huge mass of people networked on 4 machines. So we tried to go with a deterministic replication, and we'll go over it during the presentation. So next, I will let Antoine present you the 3 possible AI states.
Thank you very much, François. So yeah, now first we have our lowest resolution bulk. This is the lowest LOD we have in our system. It's always far from the player, more than 40 meters away. There's no entity, like François said, not everybody in our system has an entity. So those have only a bulk object that we call. So it's a low polygon count. There's a low animation bones also, so the animations are simple and there's not a lot of bones to animate, so we can do it pretty fast. And it has only a basic reaction system. On the other side, we have the autonomous bulk. The autonomous bulk is really close to a real NPC. It runs the full animation system. Every component of the entity is on. There is an entity, obviously, because it's a proper NPC. It's costly. We cannot have a lot of them at the same time. Maximum of 40 to 60 NPCs around you of this type. And between the two, we created the Puppet bulk. The Puppet bulk is the link between the two AI LODs that I spoke before. This NPC has the particularity of having an entity, but pretty much every component of the entity is off, so it doesn't cost any CPU. But they still have the graphic of the iRes entity. The way it's animated, it's animated by the other LOD, the Puppet, the bulk, the low-res bulk, and it's called a puppet because the low-res bulk puppeteers the iRes entity. So it's low-resolution AI with high-resolution graphics. And it permits us to do the switch between the low-res bulks and the autonomous bulks. So here we can see all of those AI LODs, one besides each other. On your left, you have the low-res with really cheap mesh, cheap textures. It's not the same shaders as the iRes entities, so it doesn't look as good, but it's far away, so it's not really a big problem. On the right, you have the autonomous bulk with full graphics quality. Obviously, in this image, it's not perfect because we don't have the old lighting of the system, but it's a fully realized NPC with a complex animation system, over 300 bones, so all the bones are there. And in between, you see the merge between the two. You can see that it resembles a lot the one on the right, but the stance is not the same. You can see that the hands are open on them. It's because we have no bones in the end, so they're not animated at all. Also, the stance look a lot like the one in the low-res bulk. Here we have a top view of where are those NPCs located in a map. You see that close in the red section, it's the autonomous bulks. So inside of 12 meters, pretty much all the NPCs will be autonomous bulks. In the greenish blue section, you have the puppet bulks, which makes the transition between the two LOD systems. And far away in the distance, you have the low-res bulks, which are really far away, 40 meters away. So here we can see performance metrics of all those LODs. The low-res will cost us less than 25 microseconds per NPC to compute. So this is really cheap. The puppet bulks, about 150 microseconds, which is not too bad. And the autonomous costs us a lot, 500 microseconds to 5 milliseconds to compute. As you can see, there's a factor of about 100 to 1 in terms of performance. Here is a bit of a comparison between the autonomous bulk and the low-res bulk. The interesting thing is that the autonomous bulk, we can have an infinite amount of variety of models. This is because our spawning system will mix and match different parts of the body. So when it spawns one individual, it's always different. So there can be, I don't know, 25 different faces with lots of different clothes, pants, shoes, and everything is mix and match so that we have a lot of different variety when we spawn a real NPC or an autonomous bulk. On the other side, the low-res bulks has only 29 meshes. So we have only 29 different models to represent everything in our world. Males, females, poor male, rich males. As you know, in Assassin's Creed, we have a lot of variety. But because they're far in the distance, we can go away with only having few of the models. Obviously, the autonomous bulks have a lot of triangles that we have to compute. They are high-quality NPCs. Low-res bulk, low count of polygons. Same for the bones. We have 300 bones for autonomous NPCs, only 11 for the bulks. And for the autonomous bulk, we have no polygon limits. If you have more people, we will render more polygons. It's different for the bulk system. In the bulk system, we have a maximum cap of polygons to be rendered. So let's say that we have tons of people on screen, and we go over that limit of 300,000 polygons. We will lower the graphics LODs of each of these NPCs so that we don't ever go over that limit. This is always to keep the frame rate high enough so the user have a good experience. So here we will see another thing that is really important in our system. It's the camera calling. Obviously, graphics does camera calling. As you can see, we don't see the people behind. But not only, we don't do calling only for graphics, we also do calling for animation and AI. What I mean by that is that the animation of the bulks behind the camera will never be updated. Only the simple state machine will be updated so that they are the proper position in the proper state. Another thing is that behind this camera, there will be no puppet bulks, neither will be autonomous bulk. All of those NPCs that are behind you, we want to reuse them so they are in front of you, so you have always the proper NPCs that you see in the camera. That enables us also to maximize the performance, the number of NPCs in screen and minimizing CPU cost. For the animation system, we could not use the same animation system that the autonomous bulks or normal NPC use because it's way too costly. The system is really powerful. The system we have in Assassin's Creed is really good. It can blend up to 30, 40 animation at the same time. There is really complex animation trees, but we cannot use that system for the bulks because we have so many of them. So we use a really simple animation system that will blend a small amount of animation at the same time, maximum 12, and really simple states moving forward, playing custom animations. We don't have different animations for male and females, which enables us to save memory and also CPU power. One of the drawbacks of that is obviously that they will have stiff hands, again, because there is no bones in the end. So it's a good telltale when you see NPCs in our presentation to know what is the type of DLOD that is running on that NPC. If you see stiff hands, it's a puppet bulk or a low-res bulk. If they have good animation in the end, you'll see that it's autonomous bulk. We'll get on that later. So here's an example of that. We see an NPC that is animated using the low-res animation system. You can see that the hands are really in a weird stance, and she's supposed to be grabbing the chair, but she doesn't because there's not enough bone to go where we want. Obviously, this happened in the distance. If you get close enough, it will be transferred to an autonomous NPC, and the animation will be properly played. Also, for the collision system, we could not use Havoc, because obviously, having 10,000 NPCs in Havoc, having each their own rigid body, it gets really, really hard on the simulation of Havoc. And what we used is a simple 2D partitioning map that we can access each of these NPCs really fast using proper coding techniques. And we slide them when they're colliding using some repulsion forces. Also, we clamp them on the nav mesh so they never go into houses or props in the map. And we can play a small crowd push behavior when we detect a collision. We'll see that in the next video. Here, all the NPCs that you see are puppets or low-res bulks. They're not in the high-res state of animation. And as you can see, when the guards pass by, they will slide a bit. There is some overlapping, but it's not too bad since it's in the distance. Also, as you can see, they play a small animation when you go by. So let François now talks about the legacy AI.
All right. So we've seen the animation system and the collision system. So I'll talk a bit about the brain. So the legacy AI, again, I won't go into details here. We really want to focus on the cheap ones. Think of it as complex behavior trees. They have lots of sensors. They know the position of everything. They have steering. They have a full pathfinding on the nav mesh. So they are super costly. So this is why we had to develop our own brain, our own cheap brain that runs on all the 10,000 NPCs. So the idea behind this brain is to have really, really small scripts. So they cannot do complex stuff. They can do a series of really, really simple stuff. So they can stand still, play one animation, go to. So really simple stuff. They also have one main goal in their whole life. So whenever a bulk is created, he has one goal. One goal in his life is to stand on a point. So we give them a point, and he has to stand on it. They cannot do complex reaction, but they can do chains of them. And also, they can never interact with NPC. That's important because all the scripts are actually playing with the bulk itself, so it can have him play an animation, have him move, but it can never start having a synchronized animation with another character. But they can actually react, but we don't have occlusion. Again, we can do recast on them because there's just too many of them. So each bulk is flagged whether it's inside or outside, so we know that an inside bulk cannot react to an outside stimulus. We do not network the reaction, so the bulks can react, and we have them react locally. What we do network is a danger source. So if there's ever a smoke bomb, we make sure that the smoke bomb is replicated, and then we assume that every bulk around it will react the same way. They can use navmesh for pathfinding, but whenever they do queries on the navmesh for pathfinding, it's super costly. So we try to have them move fixed in place or move along pre-generated paths. I'll cover that later. And also, whenever they react, they try to follow what a real NPC would do. So for example, I talk about the smoke bomb reaction. So whenever I throw a smoke bomb, you'll have the real reaction of trying to move your hands around the smoke, trying to get out, coughing, and then blending into your flea. The low bulks can do it, but it's really modular, as you'll see in the next slide, hopefully. All right, so now so this is the cheap reaction. So they play one animation, then they kind of pop into their runaway. So it's really, again, simple modular scripts that doesn't look super good, but in the distance, you get away with it. And this is the real reaction, where you actually see that now the people move their hand correctly, they smoothly blend into their flea. So this is what the player will actually see when they near him. So where are the bulks contained? We talk about bulks like this mystical entity, but they are mostly data representation. They have a mesh, but that's about it. What actually holds them is what we call shepherds. So shepherds are spawned in our world, and they contain bulks. So they hold this big bunch of people, and it's the shepherd that contains all the data needed to compute everything. So they keep track of the state, like which animation is supposed to be playing on this bulk. It's them that will compute all the bones where they should be. It's them also that runs the script that I talked about. So every time they do something weird, the shepherd will push a new script on their member. The shepherds can be of an arbitrary size. It's really up to the level designers. So each bulk inside the shepherd has a unique ID. So you can actually query it from another system. And also, the ID is unique over the network. So if we ever need to do something specific on a bulk, we can do it over the network. So they are placed by LDs. They are flagged whether they are indoors or outdoors so that we have occlusion. They also have deterministic position. This is super important because it helps us on the networking side. Every time a shepherd have all its members present, they are all at the same position on each client. And again, as I mentioned before, their whole life, the bulk, his whole goal will be to stand on that point. So if ever they moved away for collisions or small reactions, they'll always come back to their point. So we know that over time, they'll always be at the same position. All right, so also they are fixed. So shepherds have only static fixed members, no moving. So that's important. Here in the big scene, you can actually see multiple shepherds. So you see, for example, on the left, you see these squarish blobs of people. These are shepherds. On the right, you can see that the density change. So it's really up to level designers to manually place every shepherd. So whenever a level designer places a shepherd, he can select count and density. And as he selects this, we auto-generate all the position. So all the positions are generated and saved so that we know that they are always the same on each client. And they can actually manually edit the position, but obviously like manually editing 10,000 people would get crazy. We also give tools to script the shepherds. So the mission designers can never play with the individual, they can play with the whole shepherd. So they can like have a whole crowd play a rioting animation or have the whole crowd start to flee, but they can never do stuff on the individual. So on the left is what like a shepherd looks like, and on the right you see all the generated points, and again, for its whole life, the bulk will want to stand on this point. So the shepherds are static, so the city would suck, right? So to have all these standing still people, so we needed to have some movement. So what we did is we created a special shepherd that we call the wandering crowd shepherd. So what we do is we basically have a randomly generated closed paths. So the paths are random and they cover the whole of Paris. On each path there is a speed. So we know for a given time where he is on this path. So what we do is we basically give the bulk his position. The bulk always wants to stand on it, but now the point is moving in time. So he's always trying to reach it forever. So he is walking around in Paris. The system is still deterministic because the paths are pre-generated offline. The time is fixed, the speed is fixed, so we know for a given time where everybody is in the whole of Paris. Paris usually has 60,000 members running at a given point. So these are like the generated paths, and then the bulks will basically walk on it and follow random loops on it. So again, there is no pathfinding. I said it was too costly. So what they do is they basically follow the points directly. So even if you remove the whole of the geometry, they won't fall. They would continue to float in the air and walk on their path. Also, each path is selected a model. So for example, in a rich region of Paris, you will have a rich bulk there, and same thing for a poor sector, and so on. We do not do anything specific at the intersection points. We assume that our cheap collision system will do the trick, and if ever the player is close to the intersection, then it will be autonomous bulks that have like full steering and cool avoidance and everything. And the final thing we can do to have movement in our game is we can actually release like all the members of a shepherd into an empty shepherd. So, so what we do is we basically take all the members of a shepherd and assign a new position on another shepherd. So now the bulk wants to reach the point and they walk around. So I'll show you in the next video what we have now is a tavern, like a 3-story tavern. So the bulks were in the tavern and then it's closing hour, so they need to get out. So we basically take the shepherd that's in the tavern and release it into the wandering crowd. So they will get away and start moving. So they are slowly exiting the building and getting out. We can do the inverse. So it's the morning, the tavern is open again. So we can have all the members get new points inside the tavern. So they will move in and stand still on their new fixed point. So you see the people in the second story are standing still and they will not move anymore. So I'll let Antoine continue over with how we can transition into the higher states of the ILOD.
Thank you, François. So yeah, now we have all those low-res bulks having their position, moving around in the city. But what happens when you get close? We have to switch them to a proper NPC or a high autonomous bulk or a high-res model. So what we do is we gather statistics around the player or around the camera, and we check every bulk that when it's spawned, there is a tag associated to it that permits us to spawn the real NPCs that corresponds to him. So with this system, when we gather all the bulks around the camera, we can see which kind of tags we need to spawn in our pool. This pool is a really important thing because it's the one that holds all the pre-spawn NPCs that we will use to switch the autonomous bulk with. So this pool will always try to match the statistics around the player. So if he has too much female compared to males, he will adjust by spawning a female in its, it will spawn a female to have a female ready. We do that because we only spawn one NPC per frame because the spawning process is extremely costly. So by gathering statistics around and always adjusting at each frame, we can keep up with the change of variety around you. So it's constantly adjusting, and obviously when we have a lot of different models around the player, it gives us nightmares because obviously if you have only 3 people in the pool, because there's so much variety around you, it will be harder to switch to the proper models. So then we will go back to a backup method and we will switch, with any other male. And then we have this visual pop that you can see sometimes in ACU. We try, the pool is alleviating that problem, but it can still happen. So here in the next slide, I'll explain to you what are those 2 pie charts. The one on the left is the one representing the actual statistics around the player. The one on the right is the actual, what is the pool is actually composed with. You will see that those 2 pie charts will change over time. We have a video after that. And you will find out that the right will be filled up slowly to match what is the current spawned, what is the current needs around you at that moment. So here we go. We will move around in Paris. We see the statistics change, and we can see that when we go around, the pool will be filling itself. You see those bands are getting larger. That's the NPC filling them. That's the high-res NPCs filling them. That enables us to, as you can see, all the close NPCs are high-res. All the ones in the back are low-res. So we can see this pool automatically adjusting over time. François?
All right, so we have this pool of real NPCs. So now we can actually transition into our Puppet bulk state. So just to give you a reminder, because we said it at the beginning, the Puppet bulk is the one that has the high-res visual. So it has an entity on it, but actually all the components are off. And it behaves as a low-res bulk, so it's puppeteered by the shepherds. It still cannot interact with real NPCs. So I'll show the transition. The transition is occurring at 40 meters now, so where my red line is in the back. So you probably won't see much because it's far away, and that's perfect. That's the way we like it, because this transition is actually putting an entity on top of a low-res bulk. So the transition is really visual, so it's pops. And we want to have it occur as far away as possible. So when I actually get closer, now you can see it happen. And the shader models are different, so you see there's difference in color, difference in models. As we said, we only have 29 meshes for the low res, so it's a really, really graphic thing. And it's not super beautiful for the eye, but it's happening from far away, so we can actually get away with it. So when we swap, so when the player gets close to a low-res bulk, we actually query the pool. We try to get the best matching model. Sometimes the pool just doesn't have it. So for example, we need a rich male, but it has only a poor male. So we actually have to put a poor on the rich, and then this gives even more popping for the eye. But usually when the statistics are good, the pool always has the model we need. We never go as far as switching a male to a female, because that would be pretty ugly. And we also reapply color, so the shaders are different, so we need to do some color matching for the two. We basically teleport this new entity on top of the low res, and we match the hats and props. The hats is super important because it's actually where we cheat. We have only 29 different mesh, and so it's 29 mesh for the male rich, male poor, everything. So I mean, there's almost no variety. So if you would look at our crowd from like next to a bunch of low res bulk, you'll see everybody is the same. So to cheat, we have different colors, but also hats. Because actually, once you're standing inside a big crowd, what you see is heads. So if you have a hat variety, you can actually get away with a low amount of meshes. Also, we blend the animations because we go from a thing that has only 11 bones into an entity that has 300. So again, when the swapping occurs, there's a new entity there on this bulk, and this entity will not be attached to this bulk. So if I ever turn the camera away, the entity will move somewhere else. If I come back, it's probably a new entity on this bulk. So it's never one entity on top of a bulk. Also, this gives us nightmare in cinematics because, I mean, the pool and everything is using statistics around the player, but in cinematics, we move the camera like probably really fast or at different location quickly. So, I mean, if you ever do a system like this, really think about cinematics and how to actually fill your pool really quickly if you need to. So, we have the puppet bulk with the entity with components off. I mean, the other state is pretty easy. You have the entity there, so you just turn on the components. So now the full AI is running, full AVOC, full steering, full everything. This guy is mostly like a real NPC for now. It's still part of a shepherd, so it can still be referred to with a bulk ID, but it's mostly autonomous, hence why we call it the autonomous bulk. So let's see it in action. So now the conversion will occur at 12 meters, so it's a lot closer to the player. But it's not a visual transition, it's a brain transition. So don't look for glitches in the mesh, look for glitches in the behavior. So it happens at 12 meters and it's far away for not to notice really. But as with everything, the giveaway is the ends. So if you look, people on the right have like this walking stance, weird stance. So they are animated with a cheap system and they have only like the spread open ends. And when they transition, they now have like a better walk cycle. They can use their head and everything. So I'll show it in slow motion. So when he walks, he has the spread open fingers, the dead stares, like he looks like a dead person, not moving his head or anything. But when he actually transition, you'll see that now his fingers will get together. And he can actually move his head now. He has full facial animation and actually has like a different walk cycle that you can blend into. So now this guy is close to the player and he's behaving like a real NPC.
Yay, it's not a zombie anymore.
So one thing to notice is, I mean, this transition seems easy, turn on the components, but it's actually one of the hardest transitions because you need to reset every variable. For example, if like the entity was jumping, then you take this entity, put it on a running guy. In your behavior code, you need to handle this transition. And sometimes this transition can be from anywhere to somewhere really different. So you need to make sure that every jumping variable is reset to match the new state. You also need to do the same thing for the AI. So if the bulk was dead on the ground, is put on top of a fleeing guy, you need to handle the switch from dead to flee. So you need to go into all the old behavior code and make sure that you can transition directly. And by directly, I mean skipping all the transitions. For example, our flee behavior, when you start a flee logic, the real NPC will fall on the ground, get up, and run. But now, when the bulk starts running, he's already running, so don't fall on the ground. Just start your logic at the right point. So you need to make sure that all your AI states are handled correctly. And again, this conversion is costly. So make sure that resetting stuff in your engine isn't too bad. Finally, now the autonomous bulk is behaving like a real NPC, so you can actually interact with it. So one important thing to know is that if you ever interact with this entity could change at any point in time. So you can never store a pointer to this entity. What we had to develop is a special smart pointer using the bulk ID. So you store the handle with the bulk ID, and you can actually query whichever entity is on top of this bulk at this moment. We also do not do a replication of these NPCs at all. Even if they interact, it doesn't matter, because most of our bulks and civilians in Assassin's Creed Unity are actually ambient NPCs. So they are not important for gameplay. So whenever they do like a shake off end or stuff like that, we don't care if it's replicated or not. Anyway, their position will always be the same on each client. But there are some cases when they react to something important, and this is a very unfortunate thing because now we actually need replication. So what we do is we created a fallback, which is right there on this frame. We spawn a fully real NPC, not part of the bulk system, and we basically replace the bulk with the real NPC that is fully networked. This is super costly. It costs around 5 milliseconds whenever we do it, and we try to limit it because it also unbalances the NPC budget. So I'll demonstrate this. First, in Unity, we have a reaction that's the alerted reaction or yell reaction. So whenever a civilian sees me or like the player shoot a guard, they can start to yell, and when they yell, they will attract guards around them. They'll talk to the guard, point to the player, and have the guard chase the player. Obviously, this reaction is very, very important for gameplay, and it needs to be replicated. So in this specific case, we use our fallback. So this one is kind of hard to see, so I tried to build a video as much as I could, but basically, on top of the bulk here, you have debug spheres. As long as the spheres are there, this guy's a bulk. All right, so I will kill the guard, and then boom, you see the sphere disappear. It all goes fast, so I'll show it in slow motion. So he is yelling. All right, so in super slow-mo, so now he has the spheres, he's a bulk. I shoot the guard, he sees the dead guard, reacts, spawn a real NPC, replace him. The transition is super seamless because he was an autonomous bulk, which is pretty close to a real NPC already, and then we just switch it. So this is super costly, but it looks really good. So it's kind of a trade-off. And now he can do the real reaction, and from then on, he's a real guy. All right, so we talked a bit about networking, but I will let Antoine close the subject.
Thank you, Frank. Yes, so now we have the system with a lot of people everywhere, but our game was a co-op, is a co-op game, so we can play for 4 players at a time. So all of these thousands of NPCs have to be properly replicated. Obviously, it's complicated because we cannot send simply the position on everybody every frame because it would kill the bandwidth. So what we do is we use deterministic algorithms. Well, our algorithms for the bulk system is pretty simple because, like François said, everybody has a position where he wants to be. So this is basically how we replicate. When we load a shepherd, every position is predetermined in the data, and every bulk will be spawned at the same place. When we select which models is everywhere in that shepherd, we use a generated random seed that will be used for this shepherd. For all clients will use the same random seed. Hence, everybody at every position will be the same model. We use the same technique for the wandering crowds. So random seed that is the same everywhere. So we spawn everybody the same. And for the wandering shepherds, we use closed loop paths that has a definite amount of length. And by knowing only the time, which is already replicated over the network, we can know where everybody is. So obviously, they will always chase their position, so they will be always at the same position at every moment in time. So this is the way we replicate the fake crowd and all the bulks in the bulk system. Obviously, when we transfer from an autonomous to a low-res or puppet, the low-res and puppets, the bulks are replicated by their position, but the autonomous and low-res puppets will also try to be at the same position. So we don't need to replicate who is an autonomous bulk or who is a bulk puppet. This is local. So maybe a bulk is a low-res bulk on one system. It can be a high-res bulk on the other system, but they will be at the same position, looking pretty much the same. This is good when nothing's happened, obviously. When you're in a steady state, this works perfectly. You know, everybody's at the same place on all machines. Good, we've done our job. No, because there is danger source or events happening in the world. We're in a game, there's lots of stuff happening. Maybe you kill the guard, somebody reacts. So what we do is for the bulks, since they are cosmetic, we don't replicate everybody individually. We will replicate only the event or the danger source. So they will pretty much react the same, but there may be some divergence. But at the moment that this comes important for gameplay, we will fall back to our fallback, like we said before, and we will spawn a real NPC that is completely replicated over the network. Obviously, this is not perfect, but we can live with the small problems since it's cosmetic and there is so much happening that it gives a good result even over the network. So now I will switch to some fancy graphics just to show you the CPU usage for typical crowds. So our typical crowd in Assassin's Creed Unity is about 2,000 NPCs, and it uses about 20% of the resources, the CPU resources we have. So it's not that much. On the other side, when we come to a really big crowd of over 10,000 NPCs, this climbs a lot. This is because, obviously, there is so much people to calculate, and also because we tone down other systems so that we can reallocate resources from for the other system to the crowd system. So it climbs up to 50% use of the CPU for a 10,000 crowd of NPCs. This is the distribution of all of this CPU time. For the typical crowd, as you can see, 70% of the CPU is used for autonomous bulk. So our real NPCs, our autonomous bulks, costs a lot. But when you go to a 10,000 crowd, 10,000 NPC crowds, it goes around, and now it's the low res that takes so much CPU because there's so much of them. It takes about 55% CPU for the bulk system then. For the memory, pretty much everything is fixed cost in the bulk system. The pool is always 160 NPC pre-spawn, some dormant, some used, but it's always 160, so it's fixed cost memory for the autonomous bulk that are waiting there to be used. For the shepherds and the wandering crowds, all the shepherds and the wandering shepherds, it's also allocated one time. So this is another memory optimization and CPU optimization, since when we load a shepherd, we will allocate the memory for all the NPCs in there. There is no dynamic allocation anywhere else. So this saves a lot of CPU and makes the usage of the memory much more predictable. Also, it doesn't use that much memory for low-res bulks. So as you can see, there's only a 20 megabytes difference between 2,000 NPC crowd and 10,000 NPC crowd. So we can see the percentage of memory we use for the bulk system in Assassin's Creed Unity is only 5%, and this 5% is distributed mostly for graphic use, textures, meshes. Another topic that we wanted to talk to you about is the multi-threading. Obviously, if you want to do something like that, really big crowds, you have to make heavy use of every CPU cycle that is at your disposition. Modern PCs and actual console, Orbis, or not Orbis, but PlayStation 4, Xbox One, they have a lot of CPU for you to use, up to 6, even more for PCs. Even older console like PS3 and Xbox 360 had a lot of CPUs also. So we have profiling tools that enables us to detect every idle cycle that is in our frame. So as you can see here in the image, this is the view of our profiling tool. And as you can see, when we calculate the bulks, there's not much CPU left. Another interesting thing to know is that you have to limit the lux, critical sections for the technical people around here. Limit the lux, the mutex. Don't use that. And if you have to, lock for a really small amount of time so you don't starve the other CPU. And use lockless mechanism as much as possible. Another thing that we did to optimize all that is the use of a dynamic map that I talked to you earlier. This map is a map of buckets, specially repeating. It's a 2D map, so special 2D with each buckets, and it's repeating in the map. So we can allocate everybody inside that map and query all NPCs around a position really fast. We use double buffering for this map. So in fact, we don't have one map, we have two maps. One is used to make the queries. This map has been built in the previous frame. And in the current frame, when we add a new bulk on screen or in the system, we add it in the other map, the one that is currently being created. That enables us to have no remove operation. So if we remove an NPC from the world, it will simply not be added on the next frame. So this is a lot faster because we don't have remove operation, because remove operation in arrays are really slow. You have to search for them, remove them, copy memory. So we don't do that. We only use add operation in a map and query in the other map. It's only 1.5 microseconds query for 1.5 meter radius, which is quite fast to know everybody around you. So this is a bit technical. If you're not technical, don't worry about the slide. In the red rectangle on the left slide, you see that we use intrinsic operation to make sure that the loop of processing of query is really fast. And on the image of the right, the two red rectangles show that we use intrinsic operation to add to these maps. Sorry for the technical things, it's for programmers out there. So now, François will close this talk.
All right, so you've seen what we have built for the game, and what is left to do, or where do we want to go? Sorry about that. So first, I mean, the worst part of this whole system is the popping. Obviously, when you don't have the good mesh in your pool, you see popping, and that's just like it makes your eyes bleed a bit. So we want to work with dithering, see if we can actually reduce this popping and make it easier on the eyes. Also, we want to have deterministic reactions. So now we have only a deterministic position, but if we can have all the bulks react the same way, then it will keep their position easier over the network. So then everything is easier to replicate. And also, we want to support low-res interaction. So I mentioned that all the scripts only do stuff on the member itself, but we would like to have animations, like bulk animations, where the shepherd is actually moving two bulks at the same time. And if we could have this type of animation, then we could actually do fighting, and that would be pretty sick to see. And that's my personal, what I would like to see personally is big armies using our bolt system, and the player is fighting like in this field where there are 10,000 people in front of him. So that's a bit where we want to go with the technology. So let's see a video to recap everything. So this is the King's assassination mission. So this is like the biggest scene we have with the bulks. There are 10,000 individuals in this scene. And this is obviously where the system is most stressed. So this is where most of the popping will occur because the density is so big. But I wanted to show it anyway. So this is how it looks, possibly. Yes. All right. So a bit to conclude the subject. What you need to take from this presentation if you want to build a system like this in your presentation, in your own engine, is basically have a low-res system, so a system with dirt cheap stuff. So bring back your old PS1 code, really, really cheap stuff from the 90s. Yeah, so from the 90s, and have a pool with pre-spawn NPCs, and as the player gets close, replace the people with the real mesh that you have spawned. So that's about it for us. I hope you enjoyed the presentation.
Hi, first of all, very good presentation. Thank you a lot for your time that you spent here, to show us all this stuff. One question was about the example you made of the NPC that were just moving around and going to a bar and entering the different doors. Well, you have these pre-generated paths. Do you also store the direction in which the NPC needs to travel that specific closed path? And how do you do, if you had any case in which, for example, there were paths going different directions and the space was not very big? For example, did you have specific metrics to avoid these situations? Or?
All right, so for the specific example of the bar, this one is a weird case because they are navigating indoors, and in there we cannot have pre-generated paths. Because our paths are only 2D, indoors you actually need to do pathfinding query. So it's kind of a worst example, if you mean. But on paths, we basically only store like the next point, so they will be automatically orienting themselves towards the next point. So by having the points, they can move around and always face where they're supposed to go.
Also, we don't do pathfinding for them all at the same time. They will have a delay before they start, so that enables us to load balance the whole process.
Hi, thanks for the presentation as well. How do you balance root motion or translation and rotation driven by animation with replicating the low resolution bulks, like keeping track of the deterministic position without actually querying the animation system for the root motion stuff?
So the question was, if I'm...
One, do you use root motion? As in translation and rotation from animation?
Actually, for the autonomous NPC, obviously, because it's the normal animation system, Assassin's Creed Unity will use the displacement stored in the animation system. For the bulks, it's a little bit different. We go in the inverse. So because we don't need as much details in the walk cycle, we make them go at a constant speed, and we adjust the walk cycle. We have multiple walk cycles that are blended together. So there's 3 different forward walk cycle, and we blend these walk cycles so the feet doesn't slide. But it's a lot more rudimentary than the full high-res NPCs.
A question from the stream, from the internet.
Yep.
So do you allow, what types of designer controls do you allow apart from the shepherds? Do you have smart object systems as well?
Can you repeat the question, please?
What kinds of designer controls do you have over the overall system apart from the shepherds? Do you allow smart objects to be placed?
Everything is done inside the shepherd. So we don't have smart objects as per se. Maybe François, you can add something?
Right, so mostly the designers will play with the shepherds themselves and then can play with the reactions and animations they can do. But we have other types of bulks that we didn't really talk about here because it would be too long. But we have specially animated bulks that can play a very specific animation. So we use them, like those can be placed specifically, and then they will like animate a flag or do like a complex animation that requires more bone, for example.
Okay, awesome. Thank you very much, guys. Sorry. One last one.
Hi, thanks for the presentation. Just so I get this straight, you have the autonomous, which is the highest level, and you also have another NPC level, which the ones you talked that you spawned about,
No, so the new one is basically, think of it as a shepherd with only one bulk, and the animation on it is a bit more complex, and we are actually like driving a more complex animation on a 11 bone bulk, so they can do more complex stuff. But every time we use one of those, they are way more costly, obviously, because it's one shepherd for one guy. So we try not to use it, but for special animations, we can actually do something really specific.
Okay, thank you very much, guys.